on spectroscopy, just to give you a context and to get you ready for what's coming up. And we want to be thinking about why chemists do this. These are all physical methods that rely upon hitting a molecule with some type of energy, and they allow you to learn about things in the molecule. Now, the very simplest one we'll start off with, IR spectroscopy, which I think you start in lab this week, is to look at functional groups, to tell you whether you have an alcohol or whether you have an alkene or a benzene ring and stuff like that. So this is very useful. It is not as useful as, let's say, NMR spectroscopy, which we'll do next week. But this will get you to be able to differentiate. Let's say you have two compounds, you're not sure which one is which, you got mixed up. You could put them into the infrared spectrometer and then pretty quickly be able to tell which is which, right, by looking at the functional groups and getting the information out of there. Again, just a word of warning, when you do this experiment in the lab this week, I think you boil the material, you get a boiling point of some unknown liquid, and you take its infrared spectrum. Now this will be kind of busy. There are two instruments in that room at the back of the lab, so this should work in terms of everybody getting it done in time. But you've got to be careful. We're using these very expensive salt plates, which are sodium chloride, and they're polished, very fragile. Don't drop them, don't eat them. I've seen people do that. And certainly don't put them in water, right? Don't put them anywhere near water or else they'll dissolve up and we'll have to buy new ones. So then you get your output, you get a graph, and we can start thinking about what those graphs tell you. They look like this. The basic playing field is the x-axis is mostly important, and the y-axis is somewhat important when we talk about strong signals and weak signals. But the x-axis is related to wavelength and related to energy of the radiation that you put in to get that response. And in this experiment, we're seeing a transmittant spectrum as opposed to an absorbance spectrum in which the light is being absorbed or transmitted. So we'll see that spectra can be very simple, and that can be useful or not, and spectra can be very complicated. But today, what you should go home with is some idea of where to start looking on these spectra to be able to get useful information, to be able to answer questions, to be able to actually do organic synthesis. So on the left over here, I've got a really large, strong signal, and that's typically at 3300, and that will be for the OH bond. And if you look on that sheet, which should be in front of you, stapled to your hand, this is then hopefully going to correspond. You'll see that this is consistent. And if you don't see a big signal there, it probably isn't an alcohol. So as we work our way across the graph here, you'll start to see some CH bonds. Now CH bonds maybe they don't tell you that much because all the organic molecules pretty much that we deal with contain CH bonds. But you can tell a little bit in terms of sp2, sp3 hybridization if you're careful and you analyze this carefully. You move across to this sort of blank region. Not a lot shows in here which you're concerned about. In my research group, for example, we see alkynes, we see azides in that place, and that's very useful for us because it's out of the way. And then we get over here to the fingerprint region, and that gives you all sorts of different information about maybe substitution patterns, whether you have carbon-oxygen bonds, stuff like that. So these graphs are not mysterious. They are consistent, and if you practice, then this can be understood. We talked about what's happening here. I'll just put that up again because it's fun. These are the types of situations, these are the types of wagging and twisting and whatever, types of group sort of moving in the molecule that we're looking at. And we can measure those and see the graphs. Now again, just to get us started on a new week, the big word at the top, approximate, is important. They might not all be exact, but they're pretty close. All right, so if you're looking for now, at the bottom of that sheet, you'll see a whole bunch of stretching and bending vibrations and a whole bunch of numbers. So as we work our way through some examples today, we'll see again it's consistent and you can use it reliably. On the top left, you've got some detail. If you don't have an OH group, it's probably not an alcohol, and it may not be a carboxylic acid. You'll see that alcohol signals for the OH group are fairly strong, carboxylic acids are fairly weak for hydrogen bonding reasons, and then carbonyls are very easy to see, and we'll point out today hopefully some ideas that you can get very quickly and start to use this. And the key here at the bottom, certainly don't memorize that stuff. Yeah, we decided very early on that it was better to have people use it and understand it, and that helps solving problems. The actual chemistry, physics behind this, we're not that interested in, other than the fact that you have different frequencies for different bonds. That should be fairly straightforward, and they can show up on a graph. We'll look at double bonds in some detail today. We'll see that carbonyls are very important, and you can see those. And you think about the context here, chapter 13 and 14, when we did carbonyl chemistry and we did alcohol chemistry, this is all now able to measure that. We looked at these types of pictures, and you can see now that you can differentiate between an alkane, an alkene, and an alkyne simply by focusing in on the left-hand side of the spectrum. Now, what's the difference between these signals and, let's say, an OH group? The OH group is very broad. Okay, you'll see when I put some spectra up in a second that the OH group is a dead giveaway. It's very broad and it's very deep, and a lot of that is to do with the hydrogen bonding possibilities. Now, CH bonds typically can't hydrogen bonds. You get these sharp signals, and the signals we're looking at here, right there, we can see, and right there we can see. The CH bonds in an sp3 carbon are buried in that group. They're within that big signal. But when you go to an sp2 carbon with an H attached, it's shifted to the left. And you can see it differentiated from the other groups. And again, these numbers will be reliable. So down here, maybe what, 3050, something like that. And if you go all the way across to maybe 3250, you can then see the CH signal for an alkyne CH bond. So again, this is a subject that's very well understood. You can get a degree in infrared spectroscopy if you want to. You can go and learn some modern techniques. You can spend semesters worth of time studying this one technique. But for what we need to be doing is a working knowledge of what's going on. And the best way to do that is just to look at graphs. In this signal, or in this spectrum, you can see some definitions, you can see some regions that are important, and you can see now at the top a fairly simple molecule that actually does not contain anything interesting in terms of functional groups. It's all CH. So one of the limitations of infrared spectroscopy, if this is hexane, and then you went to pentane, there wouldn't be much difference in the spectrum. They contain the same groups, right? So pentane and hexane and heptane, you couldn't really differentiate between the simple alkanes because they all have the same functional groups. They all should have very similar spectra. But we'll have techniques that will allow us to do that in the near future, like mass spectrometry, which will tell you the mass of a molecule. So what you need to be looking at over here are things like the left-hand side of the spectrum is where all the single bonds to H occur. There's no OH in this one. I can tell that because I don't see this big dip at 32, 3400. If you did have that, it might be an alcohol. In this case, the CHs, it's all sp3 to hydrogen, from carbon to hydrogen. So that's showing up. There are no signals here in terms of what I just showed you for the alkenes and the alkynes. And then on the right-hand side, what you should be looking for is there's nothing here, right? Make a note of this. 1700 is one of the first places you look. And if you look on the chart, that's because where carbonyls live. And if there's no signal there at 1700, no carbonyl. So it can't be a ketone, it can't be an aldehyde, it probably can't be an ester or a carboxylic acid. And this is just a process of elimination. Once you get comfortable with, say, half a dozen signals, you'll be able to solve some problems. In the context of the course, as we are using this as chemists do to work out our answers and work out what molecules we've got, we need to do the other spectroscopies, we need to do those as well before we can do a lot of detail here. And we'll do that after the first exam. So as it says at the bottom, you're looking for triple bonds here, you're looking for double bonds there, you're looking for single bonds there. And this is very reliable. You can do this easily, and you'll see in lab this coming week, I would hope, that this is a fairly fun, fairly straightforward experiment. Now, ask questions today. I'm going to get through spectrometry, mass spectrometry today and Wednesday, and I'm going to start the next chapter. You might not see much of the next chapter on the test, but I'm going to start it. So keep the brake on. Ask me questions as we go so that we don't get too far ahead. Here's another molecule. We have changed it from hexane to hexene. All of a sudden, we put a functional group in there. And you can see that the spectrum got more complicated. Okay, there's your base sort of signals, if you like, for an alkane, and there's an alkene. We now have some important signals. They would be described as strong signals because they come quite a ways down on the chart, and they are sharp signals. They're not broad, they are sharp. We can see again CHs, that would be expected because we have a whole bunch of sp3 carbons bonded to H. And we now have these additional signals in the expected areas for the double bond. Some of which are sp2 C to H, we just talked about that earlier, and then C double bond C itself, and then some of the H's on the end of a terminal alkene. So as you practice, when you went to, let's say, pentene, you'd see a very similar spectrum. If you went to heptene, you'd see a very similar spectrum. Mr. Homan. Because, which CH? This is CH, okay? And this at the far right is partly the result of a terminal alkene, right? So it's carbon-carbon bonds as opposed to carbon-hydrogen bonds. A little bit different. Dr. Angelo. No, and that's a good thing to do today, is to get things into context. You can tell what type. That's really what it's about. It's what type. When we get to do mass spectrometry, you'll learn about the mass of the molecule, you'll learn about fragments that are logically broken into as the molecule decomposes. That tells you a lot. Once you do UV, which we'll do a little bit of later, you can tell whether you have double bonds next to each other. So you can start to put the puzzle together. And once you have carbon and proton NMR spectroscopy, which are the really fun ones and the more complicated ones, you then have 4 or 5 pieces of data which will absolutely help you work out the answer to the problem. How many of these things do you have? What type of these things do you have? All that information. So we're building up to that. Michael. Right, so that's a good question. So this here might be noise, right there. But fortunately, and you'll see there's a lot of fortunate things in these spectroscopy techniques, the ones that we are interested in tend to be strong. Okay, the only tricky one I can think of, I'm thinking of a problem on one of my tutorial things on the web, is an alkyne. So there's a signal in the alkyne, which typically shows about there. It's a weak signal, the C triple bond C. Okay, so that's a tricky one. But everything else, you can see here, the important ones that we're interested in to be able to work out, listening, Brock, that this is an alkene. You can't really tell what type of alkene it is, but it's an alkene. The signals that we are interested in are strong. And you'll see that's common as we work our way through. Okay, so this is a change of pace from mechanism. We'll get back into mechanism in about 10 days. But right now, this is all about working out what we've got. Jessica? Some of it you can. If I talk in a minute about benzene patterns, I'm probably going to save this for the next exam. I'm going to probably save this for after this first test. But if you have a benzene ring and you can't decide if it's a 1,2 benzene or a 1,3 benzene, that you'll be able to tell from some of these signals. But I'm going to save that, right? That'll complicate things this first time round. Hello? Oh yeah, oh yeah, yeah. I'll show you typical exam questions in a few minutes. Oh yeah. Let me say it again. Yep. Okay. Moving on to a different, sorry, Jessica. That's right. Give me about 10 slides. I'll give you an example. Okay, how to use this stuff. Right, so there's a simple alkene. And my point is that these things are getting a wee bit more complicated as you add the functional groups. That's the whole point. So there's the one for the alkene, and if you saw another alkene, it would typically have the same, very similar type of spectrum. And you can definitely tell an alkane from an alkene, but you maybe can't tell one alkene from the other, at least at this level. Now, you stick a benzene ring on there, you make something like T-butyl benzene, the signals get more complicated, because now you've got more possibilities in terms of the cycle. You've got some carbon-carbon double bonds, delocalization in that cycle, like you'll learn about later. But you can see here, again, we do have a T-butyl group. It does have simple sp3 carbon to hydrogen bonds, and so that's going to show up in the same place as it did for the other molecules. But now we can also see that we have some sp2 carbons in that molecule bonded to hydrogen, and they're shifting to the left, as we saw with the simple example earlier on. So that helps you out. Now over here on the right-hand side, we have a whole bunch of carbon-carbon double bonds, and this one's more complicated than we know about just yet. There's a lot going on in that cycle that we haven't learned about yet. Turns out they're not really alkenes. Leave that for later. But now, the question about substitution patterns, if you look at the bottom set of numbers, you look at the bottom right, okay, you have some numbers for what are called monosubstituted benzene, disubstituted, trisubstituted, or even ortho, meta, and para. I'm going to leave those definitions for later. You will not see this on Friday. But when we get there, you'll be able to say, okay, I have a choice between this molecule. Let's say I made this molecule with a bromine here and a CH3 here, okay, in that benzene ring. And I want to know, is it the 1,2 situation like at the top, or is it the 1,3 situation like at the bottom? And the other spectroscopies aren't helping you out because they have the same molecular mass. They might break apart in the same way in the mass spectrum as you'll see later today. Also, maybe their NMR spectroscopy or details are fairly similar, and it's very difficult to actually nail down which is which. Well, these numbers over here, at the bottom right of that chart, that will help you. So what I'm going to try and do here is get through IR spectroscopy to a point where you can handle it and you know what it's about, and then use it again and again as we head towards exam 2 in about 6 weeks, right? Because that then helps us understand where it's useful. So don't worry so much about those numbers just yet. I'm going to point out numbers that you should be concerned about. Jessica? The fact that it's a cycle, well, in this case, you might not be able to say everything, but you can certainly say from those numbers that you've got in front of you right there that that's a benzene ring. Okay, you have those two sharp signals there. That's indicative of a benzene ring. And in here, yeah, you've got some overlaps with alkenes, but there's a little trick I'll show you a little bit later with a number you can work out, an unsaturation number, which will help you. Plus, again, don't forget, this is one of 4 or 5 techniques that we have to put together. And as you get better at this, you might not look at the infrared spectrum until the end. You might look at one of the other spectroscopies and say, all right, that's a benzene ring. And then go check it with the IR so that everything can be compared. Okay. Getting into this is a bit difficult because we're doing it slowly, in a linear sense. When we get it all in front of us, it becomes really fun. Now, This molecule happens to be something called 2-hexanol. So this is an alcohol, right? This contains the OH group. So 1, 2, 3, 4, 5, 6, and at carbon 2 I have an OH. First off, some similarities to the alkane in terms of CC and CH bonds, but the dead giveaway here, all day, that's an alcohol. The argument for why it's so broad is because it can hydrogen bond. And if you have a neat sample, which is not diluted down, of course one molecule hydrogen bonds to another, and that affects the outcome of the infrared spectrum. But that is a giveaway. That tells you it's an alcohol. Now what else contains an OH group that we've dealt with? Carboxylic acid, right? So how do you know this isn't a carboxylic acid? I'll point that out in a second. A carboxylic acid also contains a carbonyl. You don't see a carbonyl in here. Carbonyls show around 1700. There isn't one. So by elimination, you can say that isn't a carboxylic acid, it's an alcohol. Brock. Then it'd be kind of fun. Then it'd be fun. Because if you have that type of situation, the amine signals will show underneath. They might even be sort of swamped by the OH group. Yeah? If you have both an amine with an NH2 and you have an OH group in there, which show in similar places, the OH for the alcohol might swamp out the other one. Then you'll need something else. You'll need some other clue to be able to nail it down. And over the next couple of weeks, that's what we do, is we put the clues together. Brianna. No, and that's another good point. That's what Brock was saying earlier. You can't tell that that's 3-hexanol or 2-hexanol or 1-hexanol just yet. You need more information. Good. All right, so this is what we should do in recitation 2, is just practice problems and look at these things and hopefully get comfortable with them and start asking questions. Now in this example, this is 2-pentanone. If I draw out 2-pentanone, 1, 2, 3, 4, 5, pentanone is a ketone, there's 2-pentanone. How do you know it's not an alcohol? Whatever that means at the back. Yeah? There's no OH, there's no big broad signal up at 3300, so there's no OH, there's no NH. A fairly flat sort of baseline at the top there. That's not an OH group or an NH2 group. Now the dead giveaway here, all right, we've got similar structures. We've got CH, sp3CH, and we've got right there, and we've got some situations over here with all sorts of different possibilities, but similar to the ones we've already seen. The dead giveaway here is that. Right? And that is a very strong signal, as they typically are for carbonyls. Now, in the lab this week, those are the signals you're looking for. Most of the examples you will get are alcohols or carbonyls, ketones, for example. And if you didn't get one of those things, you're looking for the absence of the signals. So if you don't see the signal, that can tell you it's not something. What will happen in that lab experiment is you will boil your material, and you'll get fairly close to one of a couple of possibilities. You'll have a list. And a lot of you will spend time going, okay, it could be this higher or it could be this lower, because those thermometers in that lab aren't that accurate, right? In fact, the first thing you might do is calibrate that thermometer, is find out whether you're off by 5 degrees, 2 degrees. That will help. How do you do that? Ask the TA to boil some water. Put your thermometer in, it should go to 100. If it doesn't, you've got a calibration. Put it in ice water. If it goes to 0, you're fine. If it doesn't, you know how far off you are. But when you look at your list of unknown possibilities and you've gotten the boiling point and it could be a ketone or it could be an alcohol, that's where this comes in handy. And you go into the IR room, you take the spectrum, you put the two pieces of information together, and within that limited scope of what you're trying to do there, you can work out what the unknown possibility is. So here we go. This is not an alcohol, so I can say that confidently because I don't see an OH group, and it is some kind of carbonyl. It is some kind of system in which we have maybe a ketone, and that's because that shows up about 1750. And if you look on your chart, that's where carbonyls show up in ketones. Okay? So some of you want to go into medicine and things like that, where you have to have all this information in front of you, and you have to diagnose something, and you have to come up with an answer. And this is kind of what we're doing. Now, in this example, this is a very useful way of tracking an experiment, of tracking a reaction. For those of you who will do some lab work in the future, IR is very simple. Let's say you start off with an alcohol, and we start off with this stuff, for example. Maybe I've got 2-pentanol, and I'm running an experiment and I want to turn it into 2-pentanone. What reagent would I use? PCC, PDC, what else? Sodium dichromate, because I can get away with that with carbonyls. In ketones, because ketones don't go any further. So how do you know the experiment's working? Maybe you've got some very volatile material that you can't see on a TLC plate. Maybe you have to use something like this. Well, you can take a sample of your reaction mixture and you can look for the disappearance of the OH and the appearance of the carbonyl. So over time, if you're starting with an alcohol at time equals 0, you'll have that spectrum. And as time progresses and the material converts to the carbonyl, it'll start to show the signal at 1750. And then when you're finished, all the alcohol is gone, all the carbonyl is present, the spectrum should look like this. So it's a very, very handy way of being able to monitor chemical reactions. Jessica? No, you can see both. You will see the starting material. You can take it blank, sort of standard IR spectrum, and look for changes. And then at the end, you'll see just the carbonyl, if it's all gone to completion. Catherine? A bit of both. Right? Now the spectra you will see will be pure. The only ones that you'll see in this class will be one compound. So don't be concerned about that. I'm just saying it's a very useful technique for monitoring chemical reactions. Jessica 2. You're okay? Any other Jessicas in here? Jessica at the back, what do you want? No, I'm talking to Brock D'Angelo. Brock Jessica D'Angelo right there. I didn't realize you were up there. Sorry, Jessica. No, it also doesn't help define why Seattle threw that play last night. It doesn't help define why Jim Harbaugh went to Michigan and things like that. I don't know. It helps you look at the types of bonds. Look at the types of bonds. So what we've got now are some examples. You don't have these in front of you. These are just simple examples that you can see. You haven't seen them before. And we can start to pull out interesting information. We can start to think about where this is useful and how it can be applied, and then start to think about putting it together with the other pieces of information. Now, in this example, at the bottom here, we've got a carboxylic acid. Now, that does contain an OH group. But you can notice here, this signal is not as strong or as deep as it was in the other OH groups. Now, there's something here about carboxylic acids that you can't do with alcohols. Carboxylic acids can hydrogen bond several different places. Right? When we get to mass spec, we might talk about this. Hydrogen bonding here to the carbonyl, hydrogen bonding there to the carbonyl. It's a little bit of a different pattern, and it shows up in the IR spectrum a little bit differently. So we can see here, there are signals in that region. They're not as broad as the other one for the alcohol, but it could well be an OH group. And then the dead giveaway is that. What's that? It's a carbonyl. And you can see now on the right-hand side, you've got all sorts of possibilities for benzene. Again, we'll worry about that after this first test, but all of these signals make some sense. All right? And you can tell that that's a carboxylic acid. So for a carboxylic acid, you need both of the signals, OH and suitable bond O. For the alcohol, you'd only have the one. You wouldn't have the carbonyl. So my point is, you can deduce things by saying it doesn't have this signal, so it isn't this, which will help you reinforce which choice you make. Any of the Jessicas got anything to say? Okay. Now, in this example, this is something called acetophenone. It's a simple ketone. It contains a benzene ring carbonyl with a methyl group attached, you can see. And on the left-hand side, this here isn't a hydroxyl. Okay? So we've got to be very careful with the samples that you make. If you are using the plates this week, and somebody's been in there before you, and they forgot, and they put some water in there, and your plate is absorbing moisture, that moisture is going to show up in the infrared spectrum. You're going to see some water in there. And it's going to be this big, ugly mess up here. Okay? And it might confuse you. So what do you do? How do you as a scientist work out, is that in my sample or not? Well, the answer is fairly simple. You run a blank. You run the infrared spectrum of the salt plates. Now, the salt plate should not have an infrared spectrum. The only thing you will see in the infrared spectrum, if you run that experiment, is carbon monoxide. Okay? Sorry, carbon dioxide, I should say. Because you're breathing this out, and it's a carbonyl, and it'll show up in the signal. It'll show up in the spectrum. So when you run your blank, you're just going to see carbon dioxide. But if you start seeing big OH signals in a blank spectrum, your plates are messed up. Try and get some different plates, okay? Because that will confuse things. But if that's the case, maybe there's a little bit of water in here. Maybe it was humid on the day they ran the experiment. I don't know. But you can see this isn't a strong signal. So that tells you it's probably not a hydroxyl. And then we have the similar things for in this case, the benzene ring. So we have some CH there and some sp3CH right there. And then the big signal to look for is the carbonyl again. Lack of the OH, but the presence of a carbonyl tells you it's probably a ketone or an aldehyde, but not a carboxylic acid. And when we have more data later, when we talk about spectroscopy with NMR, that will really help. Again, over here, substitution patterns from monosubstituted benzene. That will make sense on that sheet, and we'll talk about that in a bit more detail later. and some typical sort of fingerprint region signals for an aromatic ring. We have a lot more to say about aromatic rings. We don't know much about them yet. There's a ton of stuff to come on those types of compounds. Okay, another example. Here I have something called benzyl alcohol. How do you know it's an alcohol? Whatever that means at the back. Okay, there's the big strong OH signal for the OH group. It's as simple as that. If it's in there, it's probably some sort of alcohol-containing compound. And you know it's not a carboxylic acid because there isn't a big signal at 1700 that there was here. Okay, you need that carbonyl in there to be either a carboxylic acid or a ketone or an aldehyde. And again, most of these signals over here, you won't have much chance of putting together. A lot of these things are more complicated than we're interested in, but this is useful now. You can differentiate between compounds quite easily by using the technique. Volpe, you all right? Did you watch the Super Bowl? Is that why you're tired? Why was the Super Bowl on at 6:30, whereas the college football game was on at 8:30? What was that about? I got to bed like 1 o'clock when the real football was on. I don't understand that. Anyway, here's a typical question. Which of the following molecules does the IR spectrum below match? Explain your choice by pointing out important signals that help you decide by using that spectroscopy sheet, which is the last sheet of the exam. Now, you might modify that question and say, how do you know it's not the others? So that we're not guessing. So we have a choice. Could it be this? Yes, it could, because it has a big OH group right there. Can it be this? Not really, because we don't have a huge, great signal at 1750 for carbonyl. This one's a bit different. Why isn't it that? Why from that picture in front of you, isn't it this molecule? There's no alcohol on that molecule. You see the two directions we're working from? You can eliminate some because there's nothing in the spectrum that indicates that possibility. Can it be this? Yeah, because it has an OH. And can it be that? No, because it doesn't have a carbonyl in the spectrum. So we got rid of that already. We got rid of that. We got rid of that. We have two choices now. And that's typically what you'll find, is you nail it down to 2 or 3 possibilities, and then you have to take your time and work it out. So it turns out that the signal here, I think, is the giveaway for a carbon-carbon double bond. And it turns out in this molecule it's actually that one, because that would not have any carbon-carbon double bonds. It can be frustrating when you start doing this. It can be a bit mysterious, because it's something you haven't dealt with before. And it's very different to other topics we've dealt with. But once you get it all together, this is great. This is fun. Okay. We haven't seen these yet. This is a proton NMR spectrum. This is next week after we come back from the test. This is chapter 16. And this is difficult. There's a lot in here. But what you will find is that infrared spectroscopy, in an organic sense, becomes a small part of the puzzle. And you might be given the data in a linear form. And you might be given the data in a graphical form. And you have to be comfortable with both. At the top, we've got some information about a molecule that has that formula. And you might be given a mass spectrum as well to tell what fragments it's going to break into. And what you've got to try and do here is put those atoms together in a way that this makes sense and this data makes sense. So we've got to start reading these charts quite carefully. And we've got to understand that this is what chemists do. And biochemists. We've pieced together the data that hopefully give us the right answer or help us explain the outcome of an experiment. So again, you will see in the near future something like this. After the exam, we'll start putting it together like this. And 10 days from now, we'll have all the data together, and that is really quite powerful. Okay, anybody got anything to say about infrared spectroscopy? You can all do it? You can all handle that? I hope so. Mikey DeColi. You will not be thinking about the top 2 sections of that page. No. After this exam, you will have nightmares about the top 2 sections of that page. Okay? Because it's very, very complicated. Now, I'm going to spend some time on the next topic. I'm going to do a bit more on Wednesday. I'm going to talk about 16 a little bit for context, and then we'll take a test. Mass spectrometry is quite different. Again, it's the effect on a molecule of some incident radiation or some incident energy and seeing what the molecule does. With the infrared spectrometer, we hit it with infrared light from that region in the spectrum, and it bounced around. Things got, bonds vibrated faster and what have you, and you were able to see those absorbances. Mass spectrometry, I think, is quite different. This involves the destruction of the molecule. Okay, so you put a sample in here, you're not getting it back. It gets blown apart. But it gets blown apart in logical ways. So on the left, we've got your typical high-resolution mass spectrometer, which is more expensive and demands quite a bit of sort of care to make sure it keeps going. And on the right, you've got your typical sort of maybe a GC mass spec, which is a little bit less expensive. And if you're into forensics, these are the types of things you'll be seeing in the future. Mass spectrometry is an important deal in terms of working out all sorts of possibilities for drugs and for alcohol consumption, stuff like that. So these things are expensive and they're not easy to keep going, but they're very useful. And we have 2 or 3 in the chemistry department, and I think at least one of them works. So what we'll find here is mass. We'll find out that we have some mass possibilities. How big is the molecule? What are the pieces involved? And again, this is a topic that you could spend a year learning or more. People do PhDs in mass spectrometry. If you had Dr. Lescu for freshman chem, his PhD is in mass spectrometry, yeah? And he's an expert in that subject. So what's happening here is quite different to infrared. Instead of hitting it with some light that energizes the molecule, but then it relaxes and the molecule comes back as it was, you're basically destroying the molecule here. You're hitting the molecule with little bullets, and it's blowing apart. And those little bullets are electrons. So we're going to put an organic molecule in the presence of some electrons, high energy electron source, and what's going to happen is we're going to chip out an electron. Okay? It's going to pop out one electron. And if you lose an electron from this molecule, you're going to form something called a radical cation. Now, this is sort of a generic picture trying to show you where this radical got lost from, or where this electron got lost from. But you imagine all the energy levels that are involved. You've got sp3 type situations. You've got all that. It's probably from a valence shell electron. And what do you reckon about this? Stable or unstable? Unstable. Not going to last very long. And we know now that because we have a single electron, we lost an electron, so we have an unbalance now. We have an odd electron, that we can get radical type reactions. This makes sense, you know, why is there a plus charge there? Well, you lost something that was negative. We'll call it a radical cation. And that thing is unstable and wants to break apart. So what it typically does is breaks into 2 fragments. The bond will break, and you will get, in this case, a radical, because there's where one electron got picked up, and that makes sense. And what charge are radicals? Are they positive, negative, or neutral? They're neutral, right? So they're neutral. And you can imagine that radical going doing something else. It could do some other type of chemistry, either breaking apart in itself or with something else. Now, the other piece, if you take an electron away from this carbon, it becomes positive. So we're going to be interested in the sort of possibilities and the fate of the positively charged species. Okay, we're going to see how mass spec works in a second. So you can see already that's broken. That molecule isn't coming back. Now, your typical mass spectrometer inside looks something like this, where you have to generate some electrons, okay, and you hit them with you hit the sample with an electron beam, and then you break it into pieces. And so the material is traveling down this central portion. And what it's going to do is ionize and break apart. Now, those pieces that are broken apart will have different masses. And you'll imagine now that smaller pieces travel faster, and that bigger pieces maybe travel slower. So you get some separation. And you can see maybe that the effect of this can be enhanced by putting those charges into a magnetic field. Yeah? You can think about that having some effect on the fate of these things and as they travel down this tube. And you can see at the end, what's going to happen is all these little fragments that result from this destruction of this compound are going to end up at a detector from which you'll get a graph. Now, if you're interested in that, go talk to Dr. Lescu. I'm sure he'll be happy to show you the inside of a mass spectrometer. I'm sure it's very interesting. Okay? But we use it to work out masses, and we work out to use some small amount of structure. If you're an expert in this, you can work out chemical structures to to a ridiculous detail. But for what we need to do, a working knowledge of it, we need to understand what it's used for at this level. So what does the graph look like? It looks like this. The charts here are quite different to the ones we looked at for infrared. We have at the bottom some numbers which are related to mass. So M is mass. Now Z is charge. It's a mass to charge ratio. But it turns out, fortunately, for most of what we're going to do, in fact, pretty much all that we are going to do, Z is 1. Yeah, you're going to see singly charged species, and that's going to give you Z as 1. So that x-axis right there is the mass of the fragment. Well, on the left-hand side, on the y-axis, you've also got something called relative abundance. How much of each of these pieces do you have? And even for something as simple as CH4, methane, you've got a fairly complex output right there. You think about the sort of formula weight here. The formula mass of methane, carbon is 12, hydrogen is 4, so that's 16. You can see the largest signal is at 16. That's called the base peak. The base peak isn't always the mass. I'll show you some examples where the base peak isn't the mass. The base peak is, in this case, CH4, where it lost an electron, maybe became a positive charge. What do you think maybe this is down here? We have a little signal that's 1 atomic mass size higher. Any ideas? I just said C12. Now, what else is in carbon that you're aware of? Carbon isn't all C12, is it? What else is it? C13 and C14, right? And they get lower and lower in their abundance. We'll talk about C13 next week quite a lot. But maybe that's some C13, as well as the mass of the molecule. And if you're thinking now about what 15 is, what do you think you've lost to make a molecular mass of 15? A hydrogen. Simple enough. Yeah, a hydrogen, sure. You've lost an H. So you can see now that as you break off these things, you will produce some exotic species that have these masses, and then it dies away. So a very simple molecule like that can still have a fairly complicated mass spectrum. Best way to think about these things is to see them. Just to look at them and to come up with examples and think about the possibilities for the output. So in this case, there's the process. You've got the possibility now of 16, the molecular mass of the molecule, losing an H, correctly, Michael says an H radical, and you produce a fragment of 15. Now, it makes sense that the spectrum isn't much more complicated because there isn't much more you can break. But when you put a molecule together that contains many more types of bonds, the spectrum gets much more complicated, but then it also gets more useful. I'm going to ask you on Friday, engineers, listen, no calculators, but you're going to have to add things up, right? Simple arithmetic. I'm going to give you the masses of the atoms, and your job is to make sure that it matches what you're looking for. I'll show you how that works in a second. So the benzene, how many carbons? 6. What's the atomic mass? 12. What's 6 times 12? 72. And I got how many hydrogens? 6. So what's the molecular mass of this thing? 78. That's about as complicated as it's going to get, adding things up. Now, in this example, look at that. The base signal happens to be right there, and it happens to be at 78. That's benzene, having lost an electron. Now, what do you think the one above it is? There's not much of it, but what do you think that might involve? Maybe some C13. A lot more to talk about there. What do you think you've lost to get to 77? Hydrogen. Now, you can see here, this is more FYI than anything, and if you're interested in this type of subject, talk to Leslie because he's really good at this. This is way more complicated than the one that we just looked at, because that benzene ring can fall apart in different ways. You can lose carbons out of there and make 5-membered rings. You can lose carbon again and make a 4-membered ring. You can make chains. So each of these little patterns here are all about some logical process of this molecule disintegrating to become smaller pieces. You don't need to worry about that chemistry, but that's what's happening. So in that case, you can tell very quickly that it's benzene because that's the atomic mass. That's the molecular mass. That is 78 atomic mass units. That is the formula weight of benzene. In terms of complexity, that's about as complex as you'll see. In terms of interpretation, again, it's going to be a matter maybe of it is this because I see this, and it isn't this because I don't see this type of deal. Sammy, you have that look of consternation on your face. You okay? You okay? All right. Now, here's pentane. Yeesh. That's only got 5 carbons and a bunch of hydrogens, and look at that spectrum. That's very complicated. But it all adds up if you know a little bit about organic chemistry. In this example, we've got 5 carbons, 1, 2, 3, 4, 5. So what's 12 5s? And I've got 3, 4, 5, 6, 7, 8, 9, 12. That's a 72 molecule, yeah? So look at this now. That isn't the base peak. That 72 is not the base. It still shows up, and the one above it still shows up, but it's not the base peak anymore. Something has happened to this molecule to break it down so that you get a base peak, which is right here at 43. Now let's think about that molecule. What is happening to give you a molecule or a piece that has atomic mass or molecular mass of 43? We're losing something. We're losing something. Am I losing this? No, that would be minus 15, wouldn't it? And maybe that's this down here. But the important one is loss of this, where I'm losing the ethyl group. Now, if you're making radicals, why does that make more sense? Why is this more important? What type of radical will you get from this at the end? Not primary, it's the simplest example, it's a CH3 radical. And the other end of the chain might be a primary radical. And if you were to break this here instead, if you were to break it there instead, what type of radicals would you get? If you were to break this in half and this became a radical and that became a radical, what type of radicals are they? Both. Primary. Now, what was better, primary or methyl? Primary. Not by much, but enough. So primary radical here, and if you had the choice of a tertiary radical, it'll go that pathway instead. So the chemistry makes sense. Even though you're hitting this thing with high energy electrons, you can tame the reactivity of this system so that it breaks apart in sensible ways. And the biologists and the biochemists are really getting into this stuff by doing this with biomolecules. You can do this with proteins, you can do this with nucleic acids now. So why do we think it's complicated here? Well, maybe I lost my ethyl group, and then maybe I lost a hydrogen from there, maybe I lost another hydrogen from there, and that makes sense. And then maybe I lost, there's maybe the ethyl group itself, and all those things show up through some logical sort of cleavages of that molecule. Now, the best piece of information you will get out of this, no doubt, is the mass. And there will be problems coming up in recitation and on exams in which your job is to make sure you are dealing with the right number of atoms. So I might give you a molecule that has C4H5O. And you're given the mass spectrum. And the mass spectrum seems to be twice that number, because that's a reduced formula. That's the empirical formula. And you might do a very quick check, and you might realize, okay, he's playing funny here, and the molecule is actually H10. It's actually C8H10O2. It's the empirical formula was given. The actual formula, derived from the mass spectrum, tells you that that's the number of atoms you're dealing with. And then you can get into the problem. But then again, we now have differences here, some fairly common things that you can tell. How can you tell an alkane from an alkene? Simplest thing might be to do the infrared spectrum. If your mass spectrometer is working, take their mass spectra. If both are working, do both, put the answers together, and you've got a check. You've got some backup. So in this case, pentane has a formula weight of 72. To get to pentene, we take out 2 hydrogens, and you can tell that difference. You can measure 1 atomic mass unit in this technique. Down here, we don't use this much, but this is just a FYI. In this example, if you have no nitrogens, then the formula in this case is 72. It's an even number. If you put nitrogen into a molecule, 1 single nitrogen, you'll get an odd mass, because nitrogen is 15, right? It's odd. So if that's the case, you can see now 1n. In this case, you'd go back to even because you've got 2 n's, and you can use this to work out. You think about where nitrogen is, it's only 1 atomic mass unit away from carbon, right? It's next door. So how accurate is this technique? Very accurate. You can distinguish nitrogen from carbon. So again, the best way to do this is just to practice and see some things. I'm going to show another couple of slides, and then we'll have to break and skate across toward Beecher for recitation. In these examples, this is the n+1 signal. There's the big signal for decane. I think it makes sense to be at 142. And there's the n+1 signal. Maybe it's an isotope. Maybe it's a C13. And we haven't spent a lot of time, I don't think, talking about isotopes. We will as we head into NMR spectroscopy. And then you make this thing bigger. Okay, isocane is C20, and it still works. There's the parent signal, and there's n+1. So n+1 typically isn't that important to you just yet. n+2 is important. I'm going to show this, and then I'm going to finish and come back to this on Wednesday. n+2 is really important. n+2 tells you about things like chlorine and things like bromine, which happen to exist in nature in isomeric ratios, isotopic ratios. In chlorine, for example, in this example, the atomic mass of chlorine is said to be 35 and 37. there are two different isotopes. We're all aware of that, yes? Okay. And the ratio happens to be about 3 to 1. Well, that's very important because that's how chlorine shows up in nature. 2/3 of it is, or 3/4 of it is Cl35, and 1/4 of it is Cl37. Now, that probably didn't mean anything yet, but now in mass spectrometry, all of a sudden, you can see this. So there's the sort of parent signals. This one is for the molecule containing Cl35. This signal here is for the molecule containing Cl37, because that's the abundance of those different isotopes in your organic molecules if you have a chlorine. Now, where does chlorine become important? It's a leaving group. We've seen that. It can be used for Grignard reagents. We've seen that. So you can see the applications here. Why is this one? What's the ratio here? What's the ratio between that and that in terms of their size? 3 to 1. So you can see that natural abundance. The last one, which again I'm going to come back to, is bromine. And bromine happens to be about 1 to 1. You have bromine 79 and bromine 81 in nature, both of them. And you can see now on the mass spectrum, pretty close, yeah? That's very close to that ratio. And that's where that ratio comes from, probably. And you can see now the n+1 signals for both of them. And the ratio here is about 1 to 1, because the ratio there is about 1 to 1. And you have both. So have a look at that. Get some questions ready for recitation this week. I'm busy all week, but come and find me if you have questions. And we'll work towards Friday.